Good morning. Thanks for coming. A new day of this quantum toposophy workshop, and yeah, the schedule is a little bit different from which was announced. So our first speaker of today is Marsden from the University of Oxford, and who's working with Andreas Deuring, and he's going to tell us about the logical aspects of the Topos approach to quantum physics. Thank you very much.
Okay, thanks very much for the opportunity to talk. Thanks for the intro. Not thanks for closing the escape door, that helps the pressure. Hello to YouTube. My talk's entitled Logical Aspects of the Topos Approach to Physics. Might be slightly misleading title, so I'll clarify some advertising first. First of all, I'm not Nadish, as was just mentioned, and there'll be no K-theory, so if you're expecting K-theory, and this looks rather odd, that the explanations have switched around. Secondly, there's going to be no internal logic in a topos, so that's the sort of thing this will possibly hint at with a title like this. I think Sanders probably going to be getting into that sort of territory later, I'm guessing, but I'm certainly not going there at all, so we're not going to do that type of thing. In fact, given the word topos here, you think I might be talking about toposes. There's not going to be a lot of that either. So what does that really leave that I might actually be talking about? I'm going to be taking things from the topos approach to physics and looking at them from a more sort of external perspective. So as Andreas rather crudely put it yesterday, I like to rip these things away from the topos and see what I can do with them. So we're going to try and look at these things from a logical perspective. So that's where the logic comes in, and then we're going to see where that takes us. Okay, so it's a three-parter. The first part I'm going to talk about daseinisation and the so-called clopen subobjects that are important from the contravariant or Oxford Imperial school of the Topos approach. Actually, what I've got to say is pretty neutral from a co-stroke-contravariant formulation point of view, and in the second part I'll have something to say actually about the relationship between the two, so this is not really a co- or contravariant talk in particular. In the second part we're going to see things that we saw in the first part. Two important concepts are to consider all classical perspectives together, which we're all hopefully exceedingly comfortable with here now, and also the idea that once we're considering these classical perspectives, we use a notion of approximation to transfer propositions or information on how you want to look at it from one perspective to another. We're going to pursue that line of thought, and eventually that's going to help us develop a logic of, well, context and approximation, the two parts working together. These two parts follow fairly directly on from each other. The third part then, assuming I have sufficient time, really carries on from this first part, and it's going to look in more detail at this lattice of clopen subobjects again. And really what we're going to do is we're going to look at a couple of simple constructions, but they let us answer the question of, well, at least in one newish way, of what is it? Quite commonly we get asked, what are they? Is it some sort of limit? And well, in the past we've somewhat mumbled and said it isn't a product, and then carried on. Well, now we've got a sort of concrete answer there, at least in a few ways we can describe it as a limit in some order theoretic category, so that's going to flesh out the details of that. Okay, so we're going to start with a sort of fairly logical and quite general perspective. We're going to have a quick pop at Berkhoff and Norman logic and say what we don't like about it and why we're going to have to do something else. So the standard reason for not liking the idea of taking the lattice of projections or propositions on a quantum system as a foundation for a logic is the lack of distributivity, which leads to pretty poor logical properties. I mean, the lack of distributivity itself is awkward. There's no really useful way of formulating an implication, and generally you're not into pleasant territory. The second, possibly more fundamental problem is that it doesn't take compatibility into account, so you can form conjunctions of non-compatible propositions, and then it's not very clear physically what that might mean, if anything. So the question is, can we do better? My slides have dated since yesterday. They say classical logic seems too optimistic. It seems Ronnie would disagree, so this is all subjective. But we're going to go the intuitionistic route anyway. We're not going to be optimistic, we'll be pessimists. We're going to go down the route of intuitionistic logic, which obviously has many good properties, similarly to classical logic, in fact some nicer properties than classical logic in a way. And it's technically convenient because we know sort of behind the scenes that we're working with toposes, and the lattices of subobjects form lighting algebras, which is obviously the setting that we want to be to use intuitionistic logic. Okay, so we're going to view things as part of the sort of more general scheme. So the very simple idea really is that we want to start with an orthomodular lattice. That's obviously going to be our lattice of projection operators. We want to end up in some Heiting algebra, as yet to be decided which one, and we want to stuff this guy into here in some sensible way. Obviously we're going to start with a lattice of projections, that's really a given. Then we need to do one of two things. We either need to find a Heiting algebra sort of lying around, something that we're technically familiar with and looks like the right thing to do, and use that as our codomain, and that is what we're going to do. So we're going to take the lattice of clopen subobjects as the codomain for this operation. Or we could do something more possibly direct. We could construct something particular to the purpose. So the Cocker construction that was mentioned yesterday again in Ronnie's talk, and what Ronnie did was possibly in this sort of second spirit of constructing something with your specific aims in mind. So we're more pragmatic in a way. We've got an object that we think will be the right thing, and we're going to try and put our projections into there in a useful way. And then the final step in this process is obviously we've got to get things from one side to the other. So we're going to construct a mapping. That mapping is called daseinisation in the contravariant side of things. Okay, so this is mainly to fix notation in this top half of this slide. So we're going to start with some von Neumann algebra, and we're going to be working with von Neumann algebras throughout, so it's not C-star algebras. Everywhere you see n from now on, big N, that's going to be a von Neumann algebra, not necessarily a commutative. Hopefully that's that convention throughout. We're going to do the usual thing. We're going to consider the commutative unital subalgebras as classical contexts or classical perspectives on our quantum system, and we're going to denote the offset of all of them ordered by inclusion by this curly Vn. One important observation for what we're going to do later is that the projection lattice of an arbitrary von Neumann algebra is going to be an orthomodular lattice, but for each of the classical perspectives this is a complete Boolean algebra. We're going to need both the completeness and the Booleanness in what we're doing later on. The completeness is important technically rather than logically, I would say, and obviously the Booleanness gives us some logical properties when we work locally. One other thing to note is when we take meets and joins in P of V, they coincide with the ones in P of N, so it's closed under arbitrary meets and joins, which again we're going to need technically later on. Okay, so for each of these projection lattices onto a classical context, we have an inclusion map going into the big projection lattice. This guy's a complete lattice homomorphism, so we have both left and right adjoints, which we're going to denote like this. There's a mass of subscripts here, and they are necessary. We're going to use, these guys are called possibly little daseinisation, might be the right term for them, because daseinisation is used for this sort of smaller operation than a larger operation that's built out a bit later. So this guy, the little daseinisation, there's lots of these guys hanging around, and we're going to be working with several of them at once later on. So the notation's hopefully fairly straightforward. Basically domain and codomain without the projection that's written around it, so it's just this notation for that, so you can tell which direction these things are going in. Yeah, and that's just all that graphically, so nothing exciting. Okay, so some definitions, hopefully these are obvious, but I thought I'd clarify them anyway. We're going to use up arrow P for all the projections that are living above P in the big projection lattice. So we're never going to use that to mean in one of the local contexts, it's always going to be the whole show. And similarly, we're going to use down P for all the stuff beneath in the same way. And we're going to consider these guys as a rather general form of approximations to the original guys. So we're going to think of these guys as approximants from above of the original projection. So we're going to look above to sort of cruder things, effectively things that capture more space than the original. And similarly, we're going to consider these guys as approximations from below. So these are things that sit inside the space our projection projects onto, but don't necessarily cover the whole thing. Okay, so we saw these daseinisation operations as adjoints, which is one nice and fairly instructive way to look at them. This is a more concrete perspective on them, so this is turning the adjoint functor theorem, or this is actually, I believe, and Andreas can tell me if I'm misquoting, the way that they were originally reached. So I believe they were constructed on sort of pragmatic grounds originally. The notions of approximation and finding something that fitted were really how they were built, and then the existence of the adjunction came later.
Actually, Dick Walter was the first to write these things down, and then it was very much the first thing Chris and I did. And then Chris immediately said, "Oh, we can use this to construct these subobjects."
Yeah. Okay, so we can read this process as follows. We start with some projection that we're interested in finding a representative of in a particular classical context. The way to do this is we take all the approximants from above, as we're going to think of this thing. We're then going to restrict our attention to the ones in the context that we're interested in, and then we're going to find the best fit that we can by taking the meat, where we noted earlier that these projections were closed under these meats, so we're going to get something in the context that we're actually interested in. We're not going to jump out of it. And similarly, if we're approximating the other way, we take all the approximants from below, restrict, and then pick the best thing using a join instead. Now, when these two guys are discussed, this one's often preferred, and it's the one that's discussed primarily in the contravariant approach, and it's described as this sort of the sensible thing to do from one perspective. You can't describe the proposition that you're interested in, so what would be the sensible thing to do? Well, it'd be to find something cruder, sort of best fit, because you can't do exactly what you want, you have to go cruder. So it seems the sort of sensible thing to do, whereas this approach of approximating from below, I've got a proposition, I can't describe it exactly, okay, I'll find something more specific that I can say that's been seen as not very intuitive and possibly sort of counter to physical intuition. I'm not arguing for those two cases. In fact, I'm going to argue the other way later, that both of these two guys are sort of equally legitimate from another perspective. So that's possibly where we're going to some extent in the second part. But often you see this guy favoured because of this idea of approximating from above, sort of obviously been the right thing to do. Okay, what are we here? Okay, so this is pretty much a technical slide. And it's fairly intuitive. Because we're going to build our big daseinisation in a second from these little guys, we're interested in how they interact. And what this thing's saying here, if we think of these two contexts as this one's smaller than that one, so this one's got less physics, it's cruder, and this guy's bigger, it's richer, it's got more physics, then if we want to approximate some proposition, it makes sense that if we're in the cruder setting, we're going to have to go sort of further up, we're going to have less things to choose from than in the richer setting. So that's really what this is saying mathematically. We sort of flip the order here. The approximants are going to travel up relative to each other. In the cruder setting, we're going to end up higher up than we were in the richer setting. And mathematically, we just recall the definition from the previous slide, and we just see that we're restricting to a smaller set in one case, and then when we take the meats, we're going to end up higher up. I think it's the possibly other way of seeing it, not arguing semi-physical. Okay, so now we're going to think about propositions in a pre-sheet topos. I mean, hopefully all of this is familiar to nearly everybody or everybody in the room. If we're thinking of the spectral pre-sheaf as a generalised state space, then in the same way that we would represent propositions in sort of classical land by subsets, or we might think of doing that, we think about sub-objects, parts of that space, as being representatives of propositions about our system. We focus our attention on the clopen subobjects, which Andreas mentioned earlier, and others will be mentioning later, I think, as well. So these are the ones that where the sets that the functor takes you to are always closed and open clopen sets. Equally, we can consider those as projections via the Gelfand dualities. That's my one mention of Gelfand duality. That's my license gone on that front. So these clopen subobjects, you can possibly think of this as restricting our attention from arbitrary subsets to measurable subsets, although that's in no way formal. It's just a vague intuition as to why you might not consider absolutely everything. You would consider just some restricted collection of them. Okay, so
what F was.
F I've defined in slide without mentioning it. It's implicit. It basically means it's a sub-object of the spectral presheaf. So what I'm saying here is for this arbitrary sub-object, it's considered to be clopen if f of v for each context v is going to be a clopen subset.
Okay, I've still forgotten what F was.
Oh, F's new. So F's new on this slide. So that's possibly why I'm confusing you. So, so really all I'm saying here is F's an arbitrary sub-object
Right.
of, or
Right, okay,
sub-presheaf
yeah.
of sigma,
Yeah.
and then we're just working from there basically. So yeah, you haven't forgotten a definition. It's me that's skipped defining it rather than multiple. Okay, have I said everything? No, I haven't said everything. Right. This part is important because I'm going to use these guys later on. It's basically just a simpler way of describing these clopen subobjects, so I can avoid sort of pinging back and forth using Gelfand duality all the time because I really don't need it. I don't need to work and pretend I can work with arbitrary sets because we're going to be restricting to these clopen subobjects, and that basically means instead we can consider monotone functions where we've got an op here, so I mean monotone after we flip the ordering. And then the second technical condition on these monotone, well, I've got two conditions on these functions. One is that they're monotone, and the second is that they respect contexts. So what that means is, if we evaluate the function at a particular context, it's going to land in the projection lattice of that context.
There's an is too much in your sentence, so it's not that is, just that.
Oh, that.
Context.
There, okay.
That's what you.
Hope to get away with these things. There's something really wrong later on, and maybe you'll spot that. That one's minor. I will point out the really wrong thing if nobody picks me up on it. Okay, yeah, this needs to be clear because this we're going to use later on. Hopefully it's also obvious. It's basically a rephrasing of the presheaf conditions, and then we're just exploiting the fact that we know that each of these clopen subsets corresponds to a projection in the appropriate place, which is really what this is enforcing. So there's nothing really complicated gone on in this step. It's just a rephrasing to something more elementary looking. Okay, so now we're on to the big daseinisation. I'm only going to describe a sort of contravariant version of things. I don't know if this crops up in the covariant case, but you could equally define something with a bit of rejigging of definitions in the covariant case. You'd have to flip a few things around. So, no subscripts here, so this is big daseinisation now. So it's just going basically from our orthomodular lattice into our representatives of propositions inside the topos. So that's the sort of thing we described as the sort of general scheme we were aiming for earlier. And all it does is take your projection and then return a monotone context-respecting function that picks out the appropriate representative by approximating in each slot. So that's that. That's written out sort of point 3, and this is just the point-wise way of writing that out. So the function's value at v is going to be approximate at v, the original projection that we gave it. And this is clearly going to land within the appropriate context by definition. That's what we saw these little daseinisation operations did. And it's going to be monotone because of that technical slide where we saw they move relative to each other in the way that we would expect. So we're not going to find something overtaking the other one and end up with something that's not monotone. Okay, so now we're going to run through the various properties of daseinisation. So these are the positive properties, these are the things that do hold. I don't know if that's a standard term, but there's going to be some negative properties in a minute, some nicenesses that don't hold. That it's monotone is pretty obvious because it's built out of all these monotone bits, so as things get bigger, they're going to get bigger in a sensible way, so the monotoneness is fairly obvious. For injectivity, we make this observation that if we take the smallest projection in the image of this guy, it's going to get us the original back if that's the way we constructed it. That's sort of vaguely obvious because all of the projections in the image are going to be above P. It's a lower bound on them all because we're doing this approximating from above process. And we're always going to be able to find some context in which P appears, in which case we don't need to do any approximating. So P is going to be in there somewhere, so we're going to get P back. That's basically the argument. Okay, so these two guys are reasonably obvious because the top element appears in every one of the sublattices that we're going to do approximating in, so we're never going to do any approximating, so we're going to map everything to top in that case. And in the case of bottom, the same, bottom appears in every single, so bottom is the sort of trivial projection, and this is the projection onto everything, and it's not clear what my notation means. And they appear everywhere, so there's no approximating required, so you just get the whole show. Okay, arbitrary join preservation, which is obviously a nicer property and a bit less trivial than the predecessors. That follows because we know that the joins are calculated pointwise, and then we know how these little daseinisation operations behave. So we just expand definitions. We're going to look at one of these little daseinisation operations. They were left out joins, so they're going to preserve joins, so we can flip the joins on the outside, so then we can just see that the joins are going to travel through this big daseinisation operation. Which means it's got an adjoint which is actually this guy. Okay, negative properties. It's not surjective. You can imagine constructing a clopen subobject, so one respecting those two conditions, that you always land in the appropriate context and that you don't pick things so that you break the monotonicity, where you only pick either the top or bottom element everywhere. But as we mentioned before, when we daseinize a projection, the actual projection is going to appear somewhere. So this guy's not in the image of this daseinisation operation. It's a counterexample to that. Okay, it also doesn't preserve binary meats. In fact, it seems relatively hard to find not utterly trivial binary meats that it does preserve. It really, really doesn't preserve binary meat. My counterexamples here are in two-dimensional Hilbert space, which is normally a bad sign, but I think we're safe in this case. It's really just because we're constructing counterexamples and I don't want to analyse lots of cases. It's just easy to see what's going on. There's nothing fundamental about the fact that two-dimensional Hilbert space breaks it, and at 3 everything's going to get nicer in some way. It continues to behave badly with the meats as far up as you go. So if we consider two-dimensional Hilbert space, if we take two different rank 1 projections, if we take their meat, that's going to be the bottom element, so we're going to end up, when we daseinize it, as the bottom element of the whole lattice of clopen subobjects. If, on the other hand, we daseinize these two guys first and then take the meat, we're going to find some one of these sort of 4-element projection lattices that doesn't contain either of them. They're both going to get approximated to the top element, so then when we take the meat of 2 identical top elements, we're going to end up with a top there, so that guy's clearly not bottom everywhere, so that's a counterexample to meat preservation. They're really easy to find. Almost anything you try is going to be a counterexample to meat preservation. It just doesn't preserve it at all. Okay, so the image of daseinisation is also not closed under binary meats. We can take the same counterexample as we had for the previous property. And if we think about what the daseinisation of a single rank 1 projection is going to look like, it's going to be top almost everywhere, because it's only going to appear in one of these trivial projection lattices. So we're basically going to end up with something that is top almost everywhere in one projection. The only other cases we've got is everything's bottom everywhere or everything's top everywhere. But when we take the meat of 2 of these things, we're going to find 2 different Boolean subalgebras, both of which have got something that isn't either top or bottom, so that guy's not going to be in the image.
I think it's useful to give a picture.
Yeah, I might have some picture space. I'm going to need a picture for the next one, so it's probably a good idea to start with pictures. So yeah, if we daseinize one thing, if I just sort of scribble for everything being 1, we've got the trivial algebra, that's going to be top. These are all top, and then we're going to have our projection appearing in one slot here. If we daseinise another one, we're going to get a similar situation where we've got everything as top and we've just got P or Q appearing. The only other cases we've got are bottom everywhere or top everywhere. Those are all the things that you can daseinize in two-dimensional Hilbert space. So that's everything that it lands on. Whereas when we take the meat of these two guys, assuming these aren't the same algebra, we're going to end up with a sort of P living here and a Q living there and tops everywhere else, which is different to the stuff we've seen before. That's one I'm trying to skip. Okay, so the final thing is to consider what gets generated by finite meets and arbitrary joins of the image of daseinisation, and it doesn't generate the whole of sub-CL, interestingly enough. And the picture here is to consider, again, we're in two-dimensional Hilbert space. You pretty much always have to be top. So this is the sort of trivial subalgebra. In this case, what we're going to do is we're going to take a projection here in one of the sublattices, and then everywhere else, I need a new notation, everything else is going to be the bottom element now here, and I considered showing it on the slide, but it's a bit too much to work through. But if you work through, basically, in order to squash everything down here, you're going to end up needing infinitary meets, so you can't get the job done just using finite meets and arbitrary joins. So I think that's the most direct way of proving it. Sorry, you're going to have a chalky keyboard. Okay, so we're on to...
Just going back to the previous one. So,
Yep.
have you already said, is there somewhere in which that image of the daseinisation does generate the sub-CL signal?
No, see, that's what, so I'm saying the reverse. I'm saying that the image of daseinisation doesn't generate. So there are things in sub-CL that you can't get either directly via daseinising, which we've shown previously, or by taking arbitrary joins and finite meets of things. So as if you sort of build
So,
up a
for
frame.
instance, is sub-CL, is that the least complete Boolean algebra containing the image of?
Sub-CL is not Boolean.
Oh, it's not Boolean.
It's not Boolean. No, it's a complete bi-heighting algebra, and there's a vector of addresses on that, but it's not Boolean. So it's glued together out of Boolean parts, but when you glue them all together, you don't get a Boolean.
Is it the least complete bi-heighting algebra containing the image?
That I don't know.
I don't know, Steve, we would love to know something like this, so if you have any, how good that is.
I think you're getting into territory of part 3, actually, that, as I'll say again later, I don't think the lattice of clopen subobjects is any what I would describe as a sort of compelling universal property at the moment. So we've got some trivial ones because we can construct it as limits now, but they're not really the sort of thing that make you say, yeah, that really makes sense why that's the object we should be considering. So yeah, that's an open question, is to find something that's compelling, for there are other subjective definitions of compelling.
Before you go on, I just want to mention that what you generate from the image of the daseinisation by finite meets and arbitrary joins is sometimes called daseinisation topology. Presumably we will mention this in this talk.
Okay, and we can capture that via the monad induced on sub-CL, I think, can't we, as well, via that adjoint that I showed earlier. Is that correct?
Probably.
I think it's either a monad or a conad, or
Yeah.
a comonad.
Yeah.
By combining the left and right adjoint, we can capture that guy as well. Okay, so on to step 2 of my talk. Now we're into slightly non-standard territory. We're going to be basically taking these two ideas that we've seen in the first part, that is considering all contexts together, or taking interest in different classical contexts on the physical system, and we're going to be interested in notions of approximation. And this is where I probably thoroughly move to a more neutral setting, in that we're going to be considering both approximation from above and approximation from below, with no real bias between the two. And what we're going to do eventually is construct a logic using this structure that we've identified. in order to do that, we're going to need the notion of hyperdoctrine, which might be really familiar to some, in which case the next few slides might be either rather dull or very exciting if they're wrong. And for others, it might be less familiar. So we're going to run through that first. We're going to invest a few slides worth of effort just getting familiar with the notion of a hyperdoctrine. And then we're going to see that we can construct a suitable hyperdoctrine or hyperdoctrine type thing using the bits and pieces we've seen so far. Okay, so some of this I've said already, but what the key things is that we've seen sort of natural logical structure that we can exploit. We've seen all these Boolean algebras milling around. They obviously look logical. They're a nice place to get started. And we've also got adjoints milling around, and that's also suggestive of some structure that we could build some type of logic. So it looks like we've got good stuff to get started with, basically. So we're going to consider that as an instance of a hyperdoctrine once we've fleshed out what that is. That's not something specific to me, that's really, really standard. It's from Levier, I think, in 1969, so it's standard from the point of view of having been around for ages. It seems relatively poorly documented in the literature. You don't see the term hyperdoctrine crop up that much, but I think it's the right term in this case. And it doesn't Google well on the internet if you don't like NLab. NLab's got some discussion of it, but it's not like various other notions in Topos theory where you can get an absolute wodge of hits that's going to describe what's going on, so it's probably worth covering just from that point of view.
I'm trying to remember if it's in the elephant. Have you looked at it?
I'm not aware of it being in the elephant. It's implicitly in all of the big fat Bart Jacobs book, I suppose, because it's pretty much all hyperdoctrines. But I don't think he uses the term if you go to the index, so it's sort of an awkward term to find. And obviously it crops up quite a lot in the literature on the effective topos and realisability toposes, because the tripos construction, which some of you may have heard of, is basically an instance of a hyperdoctrine. Okay, so the normal sort of situation we're wanting to describe categorically is a typed logic with quantifiers. So spelling this out very explicitly, we're going to want typed terms, but terms are going to have free variables in them. So we obviously need to identify some types, but we then also need a typing context in which we can figure out what the type of this term is, because we need to know what the types of the free variables are. So those are the sort of two first basic ideas. Is we need types and we need typing contexts. Also, once we've got typed terms, we want to make statements about them. Those are going to be our propositions. Well, the terms need context to type them, so in order to form the propositions, we're still going to need these typing contexts. So propositions are going to live over typing context effectively. And finally, this is something with a quantifier in it. This is just to remind me to state the obvious fact that effectively quantifiers, they kill off things in the typing context. So you move typing context when you introduce a quantifier, because n's no longer a free variable there, so you can see yourself as moving around. The final key idea on this slide is the idea of substitution. So once you've got the slots, the variables that you've identified in your typing context, you might want to substitute some terms in there in the sort of usual way that you would see. So if we're given a term with a free variable x of type A in it, and we give them y with a free variable, and then that's a term of type B given a context with type A. Similarly, if we're given a y of type B, we then get this guy psi as type C. Then we can perform a substitution where we stuff this guy into there, and we get a term in context A of type C. So you can see a sort of composition type behaviour from a categorical point of view. I think that's really what that hints at going on there. Okay, so what we're going to try and do now is capture these notions of typing, context and substitution all together in a categorical form. So this is a thing we're going to call the base category, because it's going to be the base in some way later on. We don't really need to know what we're calling it base yet. This category is going to need products. That's basically so that we can handle the context, because we want to be able to handle lists of types at the same time, effectively collections of types. We're going to identify the objects in our category with types, or vice versa, depending which way you want to look at it. And then the morphisms are terms sorry, the terms are morphisms is probably the right way to say that. Maybe I should scroll again or something. If we think of it this way, all right, gamma for a context, then we're going to have some term T, and then that's going to be a term of type A like that. So then that's kind of how we capture the term in context. So it's basically, if we think of this as a sort of a single simple term, we have a list of types. We then have a way of gluing those together to produce a single type entity at the end, which is our term. Okay, and then for a concrete example, hopefully fairly obvious, we make the types just sets in set. Contexts are just going to be the usual Cartesian products, so we're basically taking lists of things with the appropriate types that we can glue them together. And then terms of functions, so hopefully this is a fairly obvious example. If you're given a pair of natural numbers, you can construct a rational number. You can think of that as representing a term, effectively a thing with holes in that you can put natural numbers in, and it will give you a rational number. Okay, so we now want to be able to make propositions about these terms. And as we said before, the propositions are going to vary over the context. We want ones over a particular context. So in the example of set, given a particular context, so that's all the sort of variables. Let's try and draw a picture. So we have gamma here. So gamma is, for instance, natural numbers and some real number, just as a concrete example. We're then going to take the power set of that as sort of like describing propositions or predicates on that set. In a sort of usual way, we just use subsets to identify predicates. So you can think of that as picking out the natural numbers and real numbers for which the predicate is true in the sort of usual intuitive way. So we're going to have one of these guys sort of sitting above each context, so that's kind of where the baseness comes in. So you sort of think of the base category sitting down here, and then we have fiveness, or whichever way you want to look at it, living above which capture the context in each setting. So each one of those is going to be a category with some appropriate logical structure, which probably means it's a Boolean algebra or a Heiting algebra or something like that, so we'll find in a second. We also have this notion of substitution for terms. When we make the substitutions, it's going to obviously have impact on the propositions as well. So in the example of set, that's basically going to be done by inverse images. So it's going to travel in the contravariant direction relative to the direction the term was going in. Okay, so this is most of our hyperdoctrine. Now, I'm skimming some technical details, so there are things called vector value conditions and some other details which, apart from mentioning them now, I'm not going to worry about them at all. Those would come in a second otherwise. So this is our sort of baby hyperdoctrine. The idea is we start with some base category representing our terms, types, and how they interact via substitution, and then above each one of the objects, the contexts, we have some logically structured things, so that you might think of the power set in the set example, and then we have functors going in the contravariant direction, capturing what happens substitution-wise between the propositions as well as the terms. So yeah, this is just some examples of the sort of structure you might have over here. So in the sort of most basic case, it's bool, but you might have complete Boolean algebras, Heiting algebras, distributive lattices, or whatever. So this is the sort of standard example we've been looking at up until now, really, is the contravariant power set functor, which I write as 2. And quick connection back to Topos theory for half a millisecond. When you're working with a logic inside a Topos, you're really working with one of these guys implicitly, I would say. So the subobject functor is basically another instance of this type of thing. Okay, so we mentioned quantifiers as well. They're the last important detail we're going to need for what we're describing. So if we look at this idea of a projection, so we can think of this projection introducing a notion of weakening. So we started with a proposition with a hole for a y in it, and we've added another redundant variable x that we don't really care about. It's not impacting things, so it's sort of weakening the assumptions that we've got. As we said earlier, quantifiers sort of squash variables, so we sort of expect them to be the reverse of weakening in a way. They kill off a variable and travel in the other direction. And what we've got here is, this is another Levier observation, is this quantifiers as adjoints set up, as we have the existential and the universal. Well, these are functors, but basically they're going to represent those guys in a second, so we write them the same way. And they're left and right adjoints to this weakening operation. And really explicitly, in the case of sets, these are the two adjoints. So the one for the existential, not unsurprisingly, picks out all the things where there exists something that satisfies it, and similarly the universal picks the ones where they universally satisfy it. So it looks like it's encoding the right thing if you take the concrete example of sets. Okay, so we're now back to the quantum setting finally after that detour into hyperdoctrines. So if we remember our base category here, we have a Boolean algebra living above each one of those. That's the projection lattice that we saw earlier. So we can construct a functor taking context to projection lattices, and rather trivially at this stage, taking inclusions to the inclusions over here. And then, well, the question is, if you put sort of fuzzy glasses on, does this thing look like a hyperdoctrine? Well, we've lost some contravariants up here, but we won't let that put us off too much. There's a lot of structure around that looks encouraging. Certainly the codomain is logical stuff, and these inclusion functors are preserving the logical structure, so that's encouraging. Now, this is where naming conventions cause me some trouble. Where we had contexts at the bottom before, we have contexts at the bottom again now, but where the context before, possibly you could see them as a technical device, they were capturing sort of typing information, we now have sort of physical contexts, so hopefully that won't get confusing. That's just an unfortunate coincidence of terminology. And
I mean, I wonder if it goes deeper than that. Maybe there is something.
well, I think you could.
Between the ideas of context.
I think you could. What I'm going to describe, I don't really make use of the sort of traditional notion of context, but what I'm going to describe, I think you could rephrase it so that we're still sort of context in the technical sense hanging around, so that in some sense there. But I don't know how much deeper you think of going. I'd be interested to hear.
Well, I'm just thinking the context in the physical sense is here are the things you're contemplating measuring.
Yeah. So I suppose in a way you could see, if you see types as sort of constraints on things, then our classical context is sort of a constraint as well. I don't know, there's certainly analogies in the role that they're playing, but I can't say anything particularly deep about the fact that we get that sort of clash of naming. And then the final interesting and encouraging thing is we have loads of these adjoints around, hence the horrific subscript notation that I put in earlier, is because there's lots of these guys hanging around. Between each one of these guys we've got both adjoints hanging around, so that's sort of encouraging as well. So it looks like we can sort of pursue this thing as a basis for some sort of logic. Okay, so the way I decided to structure things is to consider a situation where we have sort of typed propositions. So we have propositions in each context U. There is a collection of propositions of that type with appropriate structure in a sort of general way. And then we're going to introduce three modalities. We have this guy lift, which is going to be interpreted by the inclusion functor. So you can think of that as pushing a proposition from a weaker setting into a stronger setting. You wouldn't expect to lose anything performing such an operation, so it's just nudging things up into somewhere bigger. And we have these two guys, nabla and delta, because that kind of looks like it's coming from above, and this guy kind of looks like it's coming from below. My LaTeX skills were limited to those capabilities. So the idea of nabla is we're approximating from above, so we're going to interpret that as the left adjoint, that approximation process that we saw earlier. and we're going to interpret this guy with the other adjoint, so approximating from below. And we can phrase things more generally than just the quantum setting as a sort of collection of embeddings and then reflectors and co-reflectors would be a sort of general way to describe things. Okay, so the way such a logic would work basically is if you have proposition variables or more generally propositions that you formed by gluing together things, if they're of the same type you can glue them together using the logical connectives and you get something of the same type. So sort of doing normal logic lives within the same context, whereas the sort of physical context now as where you started. And the modalities are what let us travel around. So this lifting modality nudges us up one basically, so it takes a proposition of type U and nudges it up into the larger proposition of type V without losing anything. And these two, the nabla and delta, they take something of type U and nudge it downwards into a setting of type T, sort of representing it in some useful way, which we'll discuss possibly one way of interpreting what these two guys are doing in a second. Okay, so I think this looks sort of reasonably convincing from a quantum perspective that, as everyone's been commenting, we can reason locally using Boolean connectives, which looks sort of very nice and pleasant as a way of operating. We have this sort of straightforward operation that lets us nudge things up from weaker to stronger settings. And we've got ways of transferring back in the other direction as well to weaker settings, which we may want to do, for instance, if we're dealing with two non-compatible contexts and we sort of want to travel between the two. Okay, and right, this is the slide with the big clanger on it, which is backed. It's sort of the end point of this thing. Swap the words affirm and refute, and you're back in healthy territory. The idea is here, if we think of this approximating from above, as finding as a projection that's living above the one that we're interested in, then a successful outcome, testing that that projection is satisfied or proposition is satisfied, it doesn't tell you anything about below, so it doesn't let you affirm. But if your experimental apparatus, the bulb doesn't come on, so to speak, then that tells you it can't have come on if you tested in the other setting as well, because it was living in a subspace underneath. And similarly, if you approximate from below, you're basically finding things that let you affirm what's going on in the sort of tightest way that you can, given what you've got available to you. And again, they don't let you do any affirmation. You can't say anything in the other case. So basically, in this case, you're only interested in when the bulb comes on the experimental equipment. So yeah, this is a bit where we kind of touch on the two schemes. These two notions of approximating from above and below, they seem equally valid basically when you describe it from this point of view of affirming and refuting, rather than this notion of weakening in some sort of canonical way versus strengthening. Okay, so there's some more interesting structure around which might warrant further exploration. Is that we've got meats and we've got some structure in the context posset as well. So we might want to look at the question of transferring things between arbitrary contexts and what we can say there. I didn't really describe what a transformation of these hyperdoctrines was going to look like, but basically it's an appropriately sort of indexed thing. Unitaries induce useful, sort of meaningful transformations of these models as well. So there's more to do there, in that we can try and incorporate time evolution, and ideally I'd like to sort of fold that into the syntax of the logic rather than just being some notion of transformation of models. This is probably the main question I'd like a better answer to. I am going to go into this in a moment, but can I say useful things about SubCL as a whole, a global perspective, as you might see SubCL, using this logic that lets me reason locally, using the bits and pieces. And then there's a notion of indexed stone spaces, which I think is due to somebody here, possibly. And there's questions of duality, because again we've got sort of Boolean structure and we've got a stone structure that we might want to look at duality questions. Okay, how am I doing? I've got 5 minutes away. Okay, I'll do the turbo version.
We started a little bit late, so.
Well, I'll aim to finish on time. I think I can sort of turbo through it in 5 minutes and under explain it. It's mainly pictures anyway. Okay, so now we're interested in constructing these clopen subobjects as limits, basically. Well, I've described some of the motivation of this already, but basically the idea is we've got the sort of by definition version of the clopen subobjects as certain sorts of subobjects of the spectral presheaf. But if you're just talking to people in other fields, that makes them go a bit pale, and you've generally lost them in one of two ways. You know, you've got the topos question to start off with, which has lost half of them, and then you've got this question of Gelfand duality and things as well, which has lost the other half of them. So it's not very good for communicating with other areas to describe things in that way. We've got this cruder and quite concrete description of them as these monotone functions that respect context. That's quite handy for doing calculations, but maybe isn't very instructive on its own without you doing further calculations to see what that actually tells you. So a pretty standard question is, can we describe it as some sort of limit or co-limit? And there's this eventual aim of getting the nice universal property. Okay, so as we're doing the turbo version, I'll skip this part. I'm going to assume we know what these monotone context-respecting functions are. They come in two parts though. They're monotone and they're context-respecting. And that sort of suggests two plans of attack for constructing them as some sort of limit. Either we can start with the monotoneness and then try and pick out the ones that are context-respecting, or we can take things that are context-respecting, which is also fairly easy to construct, and then we can introduce the monotoneness as the thing that we're interested in. Okay, so we're going to do the plan A first, start with the monotone one. So we take some monotone function, little f, here, and our procedure is going to be, we're going to transform it to a new monotone function by applying the appropriate little daseinisation operation that we've seen in the last two sections at the sort of output of that function. So we're going to apply f to v, and then we're going to approximate it. And we're going to call this transformation epsilon. And it's fairly easy to show that this is monotone. And also, it's not difficult to see that this guy, the fixed points of this, are going to be the ones that are already context-respecting, because if it's already context-respecting, this is going to do nothing, it's going to become a no-op. Whereas if there's any non-context-respecting thing, it's going to have to nudge it around, it's going to have to do some approximating. And then those technical conditions we saw earlier basically mean that this is going to be well-defined as well. It's not going to break one and turn one that's sort of monotone into a non-monotone or anything bad like that. Okay, so we've turboed our way through to this point, and basically as it's fixed points, we can take this equalizer in pos, but this is just the identity, and this is the epsilon function that we described before, and that's going to give us sub CL as the equalizer of those two morphisms. Okay, so now we're going to go to plan B. So instead what we do is we take the product of all of the little projection lattices that we were interested in. That's sort of a very straightforward way of getting the context respectingness, because there's not really any way of getting out of that, because these guys will pick one in the appropriate slot. And then we know we've got an inclusion into that of the context respecting monotone functions in a straightforward way. These two guys are, well, we only really need complete and co-complete, and this inclusion map is going to be a complete lattice morphism, so it's got both left and right adjoints. Oh, and I should give credit at this point that I came up with this, and I came up with the previous one, and one of Andreas's referees, who's anonymous and therefore maybe in this room, also came up with this second plan, so it's been redundantly invented by, well, somebody else, or redundantly invented by me, depending on the timing of questions. Okay, so we've seen that this guy's injective, therefore from standard Galois connection arguments, this guy's surjective, and then again from standard Galois connection arguments, this guy's going to act as the identity. And a similar argument here for this composite is that that guy's going to act as the identity. We then know this guy's a complete lattice morphism, this guy's a left adjoint, so it's a complete joint semilattice morphism. So when we compose the two, we get a complete joint semilattice morphism, and these two form a section retraction pair in complete joint semilattices. And via a similar argument, R and I form a section retraction pair in complete meet semi-lattices. Which then means, by standard categorical nonsense, that we can form these equaliser constructions, one in complete joint semi-lattices and one in complete meet semi-lattices, where we're equalising the identity and this composite, and that gives us sub-CL as an equaliser in these two ways as well. So that's a different way of doing it by introducing the monotonicity and starting with the context respecting. Okay, and then there's a waffly conclusion, but I'll cut that as it's the turbo version. Okay, thanks very much.
Are there questions?
Yeah, I'm not completely sure that the second part of your talk, I'm not completely sure what it means completely, but somehow it seems to make too much sense to not use it. I think, yeah, what I'm wondering is if there is a nice interplay. Suppose you have this part is completely ambiguous with respect to these two approaches.
Yeah.
So Topos approaches, so both you can think of in internal terms and use presheet semantics, looking at expression, internally formulated expressions about about elementary propositions or daseinized self-adjoint elements. I think it would be nice to have to investigate how the two different kinds of presheet semantics in these approaches fit with this. I mean, when I think of this presheet-like logic of the two approaches, one is about affirmation, the other is about
Refusal,
yeah. So it seems like it would be a good idea to connect.
Yeah, I think that would be an interesting sort of thing to pursue. I mean, I think the logic I presented when I went through it fairly quickly is quite lightweight. There's not really that much going on compared to a Topos, which I know brings scary baggage in a way. So I think you'll be able to do a lot less, but what you can do, if you can make some sort of connection between the two, might be sort of easier to prove some simpler things without having to put in all baggage.
Also, it might be useful to suppose there's a nice connection in this nice logical perspective. You can also look at simpler systems, at EPRP experiments and GHZ states. You can look at simple foundational systems and see if, well, your logic gives some insight there.
Yeah, I think it probably needs the incorporation of the time evolution to be able to say useful stuff.
Well,
I think that's not difficult. I think incorporating time evolution. Well, I think Chris described it as trivial. I think yesterday, in a way, it's trivial to get some sort of time evolution in there. Getting it in there in a sort of convenient and syntactically manageable way might take a little bit.
Yeah, that will be harder, and that is definitely one of the most important challenges.
When you were originally describing hyperdoctrines, as you said, the base category normally has products, and that sort of enters into the logic with the for alls and there exists. But your base category, which is context, and this is covariant, so you have to switch it around, doesn't have the co-products, because it doesn't have the joins, and that's the idea of compatibility. So what do you see that, the existing work on hyperdoctrines in this non-Cartesian setting telling us about how to deal with compatibility of contexts?
That I have to say I've not thought about so far. It would be interesting to look at it. I don't know, I suppose as I mentioned earlier, it's quite difficult to find literature on hyperdoctrines, so if you've got any pointers then I would be interested in looking. Because the contexts are serving quite a different role in the base, I think. Possibly we can relate them to the context in the sort of technical, logical sense, but they're doing something quite different, and the relationships between them are a bit different to substitution in the normal sense. It's kind of capturing sort of strength of strength of setting in a way, and because everything's obviously it's sort of thin. There aren't multiple terms. For instance, a typical base category would be a lot richer.
Well, dualising, you can see the morphisms you've got as being maps between the spectra.
Yeah.
So you've got that same kind of flavour that sort of objects are types in some sense, and then the morphisms are maps between them, which is exactly what you get in the usual logic.
Yeah.
So, the connections aren't entirely, they don't all just evaporate. I think there's there ought to be conceptual connections there somewhere.
Yeah. Sounds like there's more to pursue there, which is nice.
I think it's a really interesting question to look at. I mean, it's not that no joints exist, directed joints do exist in the context category.
Yeah.
And
Compatible joints exist.
yes, exactly, yes. I mean, but this is exactly where the compatibility comes in a non-trivial way. And I think really there's more and more it becomes visible that as you all the talks from Oxford, that you have to look at the structure of the context category much more closely than we've done so far. Because this is what glues things together. And then this gluing together is by the compatibility structure, and that is a lot of interesting information is hiding. So I think it's a very good question to look at this more closely. And this is also what will allow you to connect with the global level.
Yeah.
Maybe one more remark. There is this. It's not always a bit negative that daseinisation, the image of daseinisation doesn't generate subCL and so on. That is true, but so vaguely we have the impression subCL is too big. That really depends on the application, of course. If you think of, let's say, measurable subsets of a measure space, and that's an awfully large collection of sets as well. And in this role, it's fine, I would argue. And there is, apart from saying, okay, we generate some smaller frame, co-frame, or some by Hunting algebra, there's another way of cutting down the size is by changing the context category to something smaller there. Immediately it becomes much smaller.
Yeah.
This is also something to look at. Maybe only between context bigger than the center or something like this.
Let's thank the speaker again.